Hello, welcome to my videos on data structures. This is part 8 of the hash table module. In this video, we will discuss a hashing algorithm called perfect hashing, which can guarantee constant access time for the hash table. Recall that we have discussed two major hashing schemes, namely separate chaining and alternative probing. In the worst-case scenario, none of these schemes can guarantee constant access time. To be precise, by hash table access, we mean search, but it does not include insertion or deletion that might trigger rehashing. For separate chaining, we might have some buckets that contain many data elements, and we must go through the corresponding linked list to find data element. For alternative probing, we might have to try many hash functions until we find the data element. Unfortunately, it is very difficult to ensure constant access time, even if we don't consider rehashing. The reason is that we need to decide the hash function before knowing the data to be hashed. In this case, there likely exists a set of data that can make the chosen hash function perform poorly. However, in many cases, we do want to ensure fast access time. If the search operation is performed much more often than the insertion and deletion operations. For example, imagine if we have collected a large number of short DNA fragments and try to find their locations in the genome. We can improve the speed of the search by building a hash table of sequence patterns of the genome. Since the genome of a species is rarely subject to change, we can expect nearly no insertion or deletion for the hash table built from the genome. On the other hand, because we have a lot of DNA fragments to search, we do want to ensure a fast search time. So, for these applications, what we can do is assume that the data elements to be hashed are known ahead of time, and then develop an algorithm that ensures worst-case constant access time. To achieve constant access time, we need to ensure no collision happens. A naive solution is to allocate a very large hash table, and in this case, we can expect a very low load factor. Then we can try different hash functions until we find one that leads to no collision. While the naive solution may work, it has two issues. First, we don't know how large the hash table should be. Second, there is no estimate of how many different hash functions we need to try before finding a good one that leads to no collision. Taken together, the hash scheme we are looking for should ensure constant access time, consume reasonable space, and require a reasonable amount of time to build. Here, we will introduce a hash algorithm called perfect hashing, which satisfies all the above requirements. The main idea of perfect hashing is very similar to separate chaining. However, they handle collisions differently. Instead of building a linked list, perfect hashing builds a secondary hash table for elements that are hashed to the same bucket. It expects to eliminate collision with two layers of hashing. In this case, the search of an element requires computing at most two hash functions in the worst case, leading to a constant access time. Here are the steps of perfect hashing. Recall that we know data elements to be hashed ahead of time. Say we have n elements to hash. Like separate chaining, we need to first allocate an array as the primary hash table. Say we allocate an array with the size of m, which is larger than n. We can simply choose a hash function to hash the n elements into the hash table, denote the primary hash function used here, h1. Then, for each bucket I that has more than one element, we will try to construct a second hash table for the bucket. If the bucket has bi elements, we build a secondary hash table with the size of bi squared. We denote the hash function for the secondary hash table for bucket I as hi2. The secondary hash function should ensure no collision in the secondary hash table. We might need to try several different functions before finding one that fits the requirement. Once we have found a good secondary hash function, we record it. Finally, after performing the above steps for all buckets with collisions, we are done. Let's look at a toy example. Say we're trying to hash the numbers 2, 12, 4, 5, 23, 13, and 3. We allocate the primary hash table with a size of 10, and we choose a simple modulo operation as the hash function. On the right-hand side, we show the result of hashing the numbers to the primary hash table using the primary hash function. We can see 2 and 12 are hashed into the same bucket, so as 23, 13, and 3. These collisions will be addressed using secondary hash tables. Let's look at bucket 2, where we have two elements 2 and 12 that form a collision. To resolve the collision, we will allocate a secondary hash table whose size is the square of the number of elements to be hashed. Say we have two elements to hash, we will allocate a secondary hash table with a size of 2 squared, or 4. We will also need to choose a secondary hash function for the secondary hash table. Say we also use the modulo operation as a secondary hash function. We then hash the colliding elements 2 and 12 to the secondary hash table and record the corresponding secondary hash function. See the figure on the right for the hash table after addressing the collision. Note that in real cases, we might still have collisions in the secondary hash table. If it happens, we need to choose another secondary hash function until we find one that is collision-free. Later in this video, we will prove that the number of such trials is expected to be a constant. We can apply the same procedure for bucket 3, where we have three numbers 23, 13, and 3. We need a secondary hash table with the size of 3 squared, or 9. We also choose the simple modulo operation as the hash function, and the resulting secondary hash table is shown on the right. Once we have resolved all collisions in the primary hash table, the construction of the perfect hashing is done. With perfect hashing, it is easy to see that we can perform the search operation in a constant time. In the worst-case scenario, we only need to compute the primary and secondary hash functions to find the element. For example, consider the case of searching 13. We first compute the primary hash function and go to bucket 3 in the primary table and find that we need to further search a secondary hash table. We then compute the secondary hash function, record it for the bucket, go to the secondary hash table, and find 13. We need to compute no more than 2 hash functions, therefore the time complexity is 01. So, this is the main idea of perfect hashing. Next in this video, we will further investigate two remaining issues relating to perfect hashing. First, recall that we may need to try several times before finding a good secondary hash function that is collision-free. And we would like to come up with an estimation for the number of trials. Second, recall that we need to allocate quadratic space for the secondary hash tables. Therefore, we would like to analyze the expected space consumption. Let's look at the first issue and estimate how many trials we need to find a good secondary hash function. In short, we would like to argue that because we allocate a large space for the secondary hash table, the chance of having a collision is low. Therefore, we only need to try a few times before finding a good secondary hash function. Let's look at this theorem. If n elements are being put randomly into m equals to n squared buckets, the probability that a bucket has more than one element is less than 1/2. Note that n refers to the number of colliding elements in a hash bucket, and m refers to the size of the secondary hash table assigned for the bucket. To begin the proof, first consider two different data elements, I and j. We say that the chance that they form a pairwise collision is 1/m. This is because if I has occupied a bucket, and we assume that the secondary hash function evenly distributes item j, then the probability that j will end up with the same bucket as I is 1/m. We also know that we have n times n minus 1 divided by 2 different combinations for the two items I and j. To estimate the total number of collisions, we can simply multiply the number of possible ij pairs and the probability that each ij pair forms a collision. The resulting number is n times n-1 divided by 2m. Since we have chosen m to be n squared, n times n-1 divided by 2m is going to be smaller than 1 over 2, which means that the expected number of collisions in the secondary hash table is less than 1 over 2. Then, based on the Poisson distribution, we know that the probability that the secondary hash table contains a collision is also 1 over 2. With the above theorem and the negative binomial distribution, we conclude that we can expect 2 trials before finding a good secondary hash function that is collision-free. Know that every trial of secondary hash function requires the rehashing of all n elements. But on average, the rehashing cost on each element is still constant. Taken together, the average time complexity for handling each primary hash table bucket is the number of secondary hash function trials times the rehashing cost, which is On. Since we only need linear time to handle the collisions in each bucket, a perfect hashing table can be constructed in linear time. Okay, let's look into the second issue and give an estimate of the space required by perfect hashing. We know that the primary hash table size will be some m larger than n, and the secondary hash table size will be less than n squared. The quadratic space complexity is of course invisible for large datasets. The tricky part is whether we can give a tighter estimate for the space consumption of the secondary hash table. To see the space consumption, we will prove the theorem. It says that if n items are being placed into a primary table size m larger than n buckets, the expected total size for the secondary hash tables is smaller than 2n. To prove the theorem, recall that when we were proving the first theorem, we have shown that the number of expected collisions of a hash table is n times n-1 divided by 2m. Although we were discussing the secondary hash table in Theorem 1, the conclusion can naturally be extended to the primary hash table as long as both hash functions distribute data elements evenly. Because we have m larger than n, the expected total number of pairwise collisions in the primary hash table can be simplified as n-1 divided by 2. Now, consider the bucket I in the primary hash table that contains collisions. Let the bucket contains bi elements. Among these bi elements, they correspond to bi times bi-1 divided by 2 pairwise collisions. For example, if the bucket has 3 elements I, j, and k, then we have 3 pairwise collisions, namely I and j and k, and I and k. Based on the algorithm, we also know that the corresponding secondary hash table size will be bi squared. Note that if we sum the number of pairwise collisions in each bucket over all buckets, we will get the expected total number of collisions, which is n-1 divided by 2 as discussed above. In this case, we have the sum of bi times bi-1 divided by 2 equals to n-1 divided by 2. Simplifying this equation, we get the sum of bi squared is less than n. Recall that bi squared corresponds to the size of the secondary hash tables. The sum of them thus corresponds to the total space allocated for all secondary hash tables. And from the equation, we know that the total size of all secondary hash tables is smaller than 2n. Taken together, we see that the total space requirement for perfect hashing is 3n, including both the primary and secondary hash tables. This bound is significantly smaller than a naive way of allocating quadratic space for the primary hash table. And it explains why we need the more sophisticated two-tier hashing scheme. Before the end of this video, I would like to add 2 notes about constructing perfect hashing tables in practice. First, although during our discussion we said that the primary hash table should have a size m larger than n, It is okay to make it even larger, such as m equals to 2n. In this case, we will have an even lower load factor, lower probability of collision, and lower probability of the need for secondary hash tables. All of them could potentially improve the perfect hashing performance. Second, while we focus on trying different secondary hash functions, we can also try different primary hash functions in practice. That is, we can try to use a good primary hash function that results in very few collisions, with the largest bucket as small as possible. Both could also contribute to fewer secondary hash function trials and a smaller memory footprint. In summary, we have discussed the idea of perfect hashing, which ensures the worst-case O1 time for hash table access. We have discussed the algorithm itself and provided proof for estimating its efficiency and space requirement. This is the last video of the hash table module. In the next module, we will discuss the tree data structure. Thanks for watching and see you next time.